In laser materials processing, we usually have all states of matter present: solid, liquid, gaseous. In this session, we will take a closer look at the liquid phase of matter, and especially on the dynamics of this liquid matter. So, in more detail, the content of this session deals with an example in motivation, which is humping, that is a periodic melt oscillation in welding. Then we'll take a look at Marangoni convection. I'll show you an experiment to it. And then we take a look at the theory. How do we describe all this? But this is very fundamental, very shallow in time here, so I just touch that a little. And we'll get immediately into some applications in polishing of glass and polymers, or in the formation of pores in a melt pool. So as a motivation, you see here a picture of a melt pool. Here the keyhole of a deep penetration weld. Imagine the laser coming from the top. And here in the back you already see a change in melt formation, a little droplet. And if we start the motion of this slow motion video, you see the dynamics, how the melt is expulged in certain time intervals. And as a result, we will, if you would see the recast in the back of that, you would see a periodic recast, a wavy structure, which we call humping. Now, where do these melt dynamics come from? In the right-hand picture, you can see the general situation during welding. In this case, we don't have a keyhole welding, we just have a heat conduction weld. So laser radiation is absorbed here in the surface, very thin layer, and then by heat conduction, the heat penetrates the surface and it forms a melt pool. The dotted lines represent the melt pool. This here is solid material. Now, usually in first order, independent of the intensity distribution of the laser, we have a highest temperature in the center of the processing zone. That is simply because we have heat conduction to the edges, so temperature will decline to the right and the left out of the center of the melt pool. Then usually, if we consider the surface tension of that melt pool, with increasing temperature, the surface tension declines. We have smaller surface tensions for higher temperatures. In other words, the decreasing temperature to the edge of the pool will lead to an increased surface tension as we approach the edge of the melt pool. In equations, this is sketched in the left-hand side of the picture. You see that the derivative of the surface tension contains of two dependencies. One is a temperature dependence with a constant concentration, and the other one is a concentration dependence with a constant temperatures. We have two partial derivatives because we have two dependencies, the temperature and the concentration. So, and usually this d sigma by dt is negative. In other words, we have an increase of surface tension with lower temperature. In this experiment, which I show you in a second, let me show you the results first, because it will happen very quickly. Now, what we do is we have a glass bowl full of water, and I poured some pepper on the surface of that water, which you see as a little black dots here. And then we take just a little tiny drop of turpentine, which we colored with some red in order to better see what's happening. And of course, the surface tension of the turpentine is way smaller than the surface tension of water. So as soon as the turpentine is deposited on the surface of the water, it will have a smaller surface energy, and the tension outside will be higher than where we have the lubrication with the turpentine. In other words, there will be a gradient in surface tension towards the edges of that bowl. And as a result, as soon as we let this drop fall onto the surface, it will spread out, it will collect all the pepper particles, as you can see on the right-hand side. So the red turpentine drop is equalized over the surface and pushed all the pepper particles towards the edge of that glass. So it is a very intense process, and small gradients of surface tension already lead to considerable forces driving the melt. So, as described, what I do first is I pour some pepper in this bowl of water so you can see the surface and you can see where the pepper is distributed in the water. And now I take a little pipette of turpentine, colored turpentine, and now 3, 2, 1, 0. So as a consequence, if you sketch the surface tension over the temperature, as I said, usually we have a negative gradient, so the temperature, for smaller temperatures, we have higher surface tensions. However, if we change the concentration and the chemistry of the process, for instance by adding some sulfur to an iron alloy, we may induce a behavior which changes in direction. On the right you again see the expressions for the surface tension as a function of the concentration and the temperature, and typical values for the surface tension that arises is something like 5 × 10⁻⁴ Newton per meter and degree. Now, what does that mean for practice? Here on the right you can see a cross-section of a heat conduction weld. So again, the radiation was absorbed only in the surface and we had heat penetration in the typical spherical way of a three-dimensional heat conduction. So this is the melt pool, which you can see here. And now if we take a look into the melt pool, we see two circular solidified melt motions. And the left picture explains their origin. As I told you before, the temperature is highest in the center of the melt. The surface tension increases with decreasing temperature, and that results in a motion of the surface particles towards the edge of the melt pool. And of course, as a consequence, if we have a flux towards the edges, we need to compensate for this change in density. So as a result, out of the center, we have an upstream of melt, and consequently, to close the loop, along the melt pool edges, we have a decline of the melt. It will just flow downwards. So as a result, we'll have a circular motion, and this will be symmetric, left and right, due to the symmetry of the heat and energy deposition. So this is the explanation how these circular motions form, and that's why we have here these circular motions of the melt which are solidified in this cross-section. If we look at the fundamentals of the melt flow, of course we can start with the very fundamental equations of motion, and in this case it is the conservation of mass. So there's no change in mass in a system. However, of course, the densities change, and this can be done by two effects: local changes of the mass, or we have a local mass flux. If we look at the momentum usually is not conserved, at least not if we have external forces, but the corresponding change of the momentum in time has to be equal to the external forces that we apply. In this more simplified case of an incompressible Newtonian fluid, the equations can be simplified as follows. So the divergence of the velocity is then 0, and the inertia per volume can be expressed as the sum of 3 terms. One is the pressure gradient, one is the momentum diffusion due to friction, and one is due to the body forces in the individual volumes. Now, all of these equations are quite complex, and they only in very special cases can be solved analytically. So what people usually do is they take the equations, take the boundary conditions, put it on a computer, and get wonderful colored pictures of the behavior of the melt. But that describes it completely and very well. As an example, I picked 2 cases in which melt formation plays a dominant role. In this case here you see the polishing of a polyamide disc. It is a plastic disc of maybe, there's no scale, say 3 centimeters in diameter. And on the left hand side you see the result when it is grinded. So as it comes out of production, it has typical roughness values of Ra somewhere between 100 and 150 nanometers. Now, if we polish it, in this case with CO2 laser radiation, with a linear intensity distribution, a line intensity distribution of a CO2 laser, and optimize the process parameters, we can get down the surface roughness to values below 10 nanometers. In perfection, we can get it down to about 1 nanometer. In glass, even lower. So now let's start the process. On the right you see a polymer disc of about maybe 2 to 3 centimeters in diameter and a CO2 laser with a line distribution of intensity now is scanned over that surface. It will start from the top and move to the bottom. And you see it in real time. That is the real processing speed of the polishing process. And it's contact-free, extremely precise, and we result in surface roughnesses, Ra values, just a few nanometers in size. Another example is the formation of pores in a melt pool. Here in this sketch you see a top view on a deep penetration weld. This deep penetration weld has in consequence a melt pool, here the blue part. And now if you look at the forces heading here in the beginning, when on the top, when the keyhole hits that very, very thin melt wall, then periodically the melt will form and will be pressed out of that front zone towards the left and the right. And as a consequence, as a result, you can see a periodic motion of the melt along the boundary condition between liquid and vapor. And as a result, when they meet on the back side of the capillary, it may happen that a pore detaches and this part of the gas freezes in and results in pores in the weld. As a conclusion of this session, we learned about the melt dynamics, the driving factors, the forces, the acceleration in melt, the friction, and the resulting resolidification of melt in terms of wavy structures like in humping in welding or in pores in deep penetration welding. If we know all these influences quantitatively and can correlate them with the laser parameters, intensity, time, beam distribution, then we can produce structures in melt-dominated process with ultimate precision.